Okay, good morning everyone. Thank you for coming to my presentation. My name is Luis Baiten. My advisor is Professor Nico Dutt. I am from the University of California at Irvine. The title of my talk is EROC Embedded Arrays on Chip for Low Power Distributed Dynamically Managed Reliable Memories. And I will try to give you an overview of my work. If you want to know more, please come to my poster. The key idea of this piece of work is taking RAID-like policies and applying them to an embedded SoC environment for distributed scratchpad memories. And the motivation for my work is that we're seeing this move towards multi-core platforms, and as a result, we're seeing distributed on-chip memories. So it's expected that by 2014, up to 94% of on-chip area may be memories. So one of the existing techniques that we are using to save power consumption is voltage scaling. So let's take a look at the effects of aggressive voltage scaling in our memory subsystem. In this figure, we have on the X and Y axis our memory array. On the Z axis, we have voltage. And we have these lines here that represent parametric manufacturing errors. The idea here is that at overdriven VDD, we do not see many of these errors propagate. As we start voltage scaling our memory subsystem, we start seeing that these errors start to manifest themselves more and more. So we are indeed saving power, but we are intentionally introducing these errors into our memory subsystem. Moreover, with technology scaling and environmental factors combined with voltage scaling, we are increasing the vulnerability of our memory subsystem to soft errors. So we are reducing power consumption at the cost of introducing errors into our memories. Now, related work in memory reliability has focused on memory characterization or ECC-based approaches, redundancy, or ECC and replication hybrids. Now, memory characterization and based-like approaches are very expensive, and they're tied to a given voltage, so they're very static. ECC and duplication hybrids incur both power and performance overheads. So if we look at outside of the box, we look at storage systems. In this case, we have RAID systems that have been deployed very successfully. And the idea of our work is, can we take these RAID-like notions and apply them to an on-chip environment? Now, let's take a look at traditional RAID systems using storage systems. In this case, we have our CPU, our system bus, and our distributed hard drives. We have a hardware RAID controller. The idea here is that we have guaranteed 24/7 uptime under really heavy I/O loads. Again, we can have a hardware or a software layer managing our hard drives. And we have different RAID levels, each one for different performance and reliability requirements. So let's take a look at what we need to do to take some of these notions and apply them to an embedded SoC environment. So we have our chip multiprocessor here with our set of CPUs and our distributed scratchpad memories. Just like in traditional RAID, we can take a hardware or software layer and introduce it into our chip multiprocessor. And in this work, we present our EROC framework, which defines the concept of embedded arrays on chip, which is composed of a set of ideas that include the idea of support for different platform configurations, be it chip multiprocessors, NOCs, and so on. Custom embedded RAID levels for use in embedded systems. We define logical scratchpad memories through an address virtualization layer. We define allocation policies for efficient utilization of the scratchpad memory space. And we employ aggressive voltage scaling to reduce the power consumption of our system. And we take all of these concepts and implement it in our EROC manager, which we have here in our chip multiprocessor. And again, it can be a hardware or a software layer. Now, let's take a look at the case for E-RAIDs or embedded RAIDs. We can take our scratchpad memory, a 2 kilobyte scratchpad memory running at nominal VDD, and compare that to a a sample array configuration. In this case, what we have done is we have partitioned our scratchable memories into smaller scratchable memories. And we have striping support, so that means bi-level access for performance. And we have mirroring, array level 1 mirroring on top of that for reliability. Now, we provide the same memory space, parallel IOs, and the memories here at voltage scale. Now, let's take a look at the effects of voltage scaling in our memory subsystem and how it compares to the baseline scratchable memory. So, in this graph, we have on the y-axis the probability of failure on the left side. On the right side, we have power reduction percentages. And on the x-axis, we have different voltages. We see that at high VDD, our array configuration incurs high power consumption overheads due to the parallel IOs to the multiple memories. However, as we start aggressively voltage scaling our memories, we see that we start seeing power reductions, power consumption reductions, up to a 46% saving. But this comes at the price of increasing the probability of failure for the memories. So we're introducing errors into the memory subsystem. However, we have these array levels in place that automatically handle these errors. Okay, now let's take a look at what it would mean to take RAID-like notions and apply them to an embedded SoC environment. Now, if we were to take just traditional RAID and implement it, we first have to statically define the set of RAID levels that make sense for a given application. We will have to allocate entire scratchpad memories to a given RAID level. Just like in traditional RAID, you allocate entire hard drives. And this greatly limits our scratchpad memory utilization. In this example, we have two applications, application 1 with 1 kilobyte of space requirements, and application 2 with 2 kilobytes. Application 1 runs on 2 CPUs, and application 2 on a single CPU. Now, application 1 is asking for mirroring level. That means that you need a minimum of 2 scratchpad memories. So in this case, we are able to successfully allocate the level. However, if we look at application 2, which requires the parity level, which requires a minimum of 3 scratchpad memories, we are unable to allocate the space because we do not have enough real estate. This leads to inefficient scratchpad memory utilization. Now, let's take a look at embedded RAIDs, which is our approach. We define the first set of array levels that make sense for using embedded SoCs. And we can take the same example for the given applications, the same requirements. And what we do is that we define the idea of logical scratchpad memories, as you can see here, that are supported by an address virtualization layer that allows us to transparently utilize the real estate. And we associate them with an array level. So in this case, we have mirroring and parity. We expose them to the outside world through our AROC manager. And the programmer sees our logical scratchpad memories as regular scratchpad memories. So their use is transparent. And we define our allocation policies for distributed scratchpad memories. And these policies allows us to utilize efficiently the on-chip real estate. And in this case, we are able to see that we successfully allocate both array levels for both of our applications, where in the previous step we could not. So this allows us to have transparent and efficient utilization of this scratchpad memory space. Okay, now I will summarize some of the experimental results, but please come to my poster if you want to know more about them. In this case, I'm going to be looking at power and performance comparison. We have our CMP platform. We have our baseline scratchpad memory running at nominal BTD. All of the other memories are running at our voltage scale at BTD equals 0.65. And we have media benchmarks. In this side, we want to look at the normalized power consumption for various approaches. We have the nominal scratchpad memory running at nominal BTD, which is our baseline. We have traditional approaches, ACC duplication, and we have a variation of our approaches. In the y-axis, of course, we have the power consumption rates. So we see that Traditional approaches incur high power consumption overheads, an average of 64% increment, whereas our approach is able to save power by up to 76% on average. Of course, this comes at the cost of performance. So in this case, we see normalized performance. On the y-axis, we see our performance overheads and the same configurations, or the same points of comparison in the x-axis. And in this case, again, we see that traditional approaches incur high performance overhead, an average of 9.2%, and our approaches have minimal performance overheads, an average of 2.3%. So in the end, we have power consumption reduction with minimal performance overhead. In conclusion, this paper introduced the notion of embedded rates on chip, or EROC. The paper introduces several ideas. I will summarize a couple of them here. First, reliability via redundancy using array levels. Second, custom array levels for use in embedded SoCs. Third, dynamic allocation policies for efficient utilization of the on-chip distributed scratchpad memories. Fourth, virtualization support via logical scratchpad memories that allow the programmer to transparently utilize the address space. We believe that we are the first to use RAID-like policies to achieve a fully distributed, low power and reliable memory subsystem. Our experimental results show that EROC can attain an average of 76% power reduction over traditional approaches with minimal performance overhead. Now, this is a very short presentation, so if you would like to know more, please come to my poster. Thank you.